All right, so welcome to Unit 1, Atomic Structure and Properties. Today we're going to be talking about moles and molar mass. So when we're dealing with the molar mass and moles of an atom, we are talking about counting atoms, really. We can use those numbers to help us to figure out how many atoms are in a substance. Now, it's impossible to count the atoms directly because, well, first of all, they're too small. We can't see all the individual atoms in a substance. We also can't count them, they're just too numerous. But we can find the number of atoms in a given substance by finding the mass of that object. In order to do this, we have to know the average mass of one atom of that substance. The average mass is called the atomic mass. The way they find the atomic mass is based on carbon. Carbon is kind of like the standard one, but the atomic mass is basically our average of all the masses of all the isotopes of a given element. So scientists can compare atomic masses using what's called a mass spectrometer, and that helps them to determine what the atomic mass is of a given atom. In a mass spectrometer, the atoms are turned into ions. This is fine because losing or gaining electrons doesn't really change the mass of the atom because electrons don't really weigh enough to contribute to the overall mass of the atom. They're turned to ions because we basically pass them through this electric or magnetic field inside of the mass spectrometer, and that the fact that they're charged allows them to be pushed through that magnetic field and kind of deflected inside of there. So the ions with more mass are deflected less. They kind of stay on their original path, but the ions with less mass are deflected more. So here's a diagram. This is what a mass spectrometer looks like on the outside. So on the inside, you have your source. This is where you put your element or isotopes, I guess, your sample, and it ionizes it, turns it into ions, takes away or gives it some electrons, and then it passes it through this magnet here, or this magnetic field or electric field. And the heavier the atom, the less it's going to be deflected. So this heaviest atom here didn't get deflected much at all, but the lightest one got deflected the most. So these are the molar masses of the different isotopes contained in our source. You can kind of think about this like just this idea that the heavier mass won't deflect as much. I mean, consider throwing like a paper airplane versus a bowling ball, right? The bowling ball is not going to get pushed as far as the paper airplane because it has a lot more mass. And so that's kind of what's happening here. The more mass it has, the more it's just going to stay on its own trajectory. And the less mass it has, the more it's going to be influenced by this magnet. So like I said, the atomic mass is basically an average of the masses of the elements and their isotopes. But it's not a true average because it's weighted by how common each isotope is. So every atom has these different isotopes, which means it has the same number of protons but different numbers of neutrons. And the more common that isotope is, the more its mass factors into the overall average. So carbon has two isotopes, carbon 12 and carbon 13. And most of carbon is carbon 12. Most of the carbon we find in nature, 98.89% of carbon is carbon 12. The rest, 1.11%, is carbon 13, so not very much. What this means is that when we find the average atomic mass, it's going to be closer to 12 than it is to 13 because most of carbon is carbon 12. So in order to find the average atomic mass of carbon, we take these percentages and turn them into decimals. So we took 98.89 and turned it into 0.9889, just dividing it by 100 to get rid of the percent, right? We multiply that by the mass of carbon-12, which is 12. And then we do the same thing with carbon-13. I guess I forgot one of my ones here, but we change that to 0.0111 and multiply it by the mass of carbon-13, which isn't exactly 13, it's 13.0034. And then we add those together, and that gives us a weighted average of 12.01, which if we look on the periodic table, is the atomic mass of carbon. And so that's where they get that from, is using this type of calculation. Example 1 says, a pure sample of silver was vaporized and injected into a mass spectrometer. The relative number of silver 107 atoms was 51.84, and the relative number of silver 109 atoms was 48.16. The mass value for silver 109 is 108.90476 atomic mass units. Find the mass of silver 107. Okay, so we know the average atomic mass of silver if we look at our periodic table. So the average should work out to 107.87. We also know the relative number, which is basically our percentage for each of these isotopes. So for silver 107, it was 51.84. I'm going to turn that into a decimal as 0.5184. And we do not know the mass of silver 107, so I'm just going to put an X for now. Plus, we know the relative number of silver 109, which was 48.16. Again, we turn that into a decimal. And we do know the molar mass, the atomic mass of silver 109 is 108.90476. And we know this all is going to equal out to 107.87 because that's our average from the periodic table. Okay, so we can do some math here to simplify this. So when I multiply these two together, I get 52.44853242. I'm just going to round that to 4 sig figs because this only has 4 sig figs. Now it's a pretty simple algebra problem, right? I can subtract this from both sides. Getting 55.42. Remember, we use our decimal places as our sig fig rule for subtraction. Then we divide this by both sides to get X, which should be the molar mass of silver 107. And it should have 4 sig figs. So we get 106.9 atomic mass units. Okay, so moles we learned about last year too, but moles are Avogadro's number, right? 6.022 times 10 to the 23rd. That comes from carbon, so we get the number, Avogadro's number, from the number of carbon atoms in exactly 12 grams of pure carbon-12. And that works out every time to be 6.022 times 10 to the 23rd. So that's where that number comes from for the mole. We can use that relationship to find the number of atoms or molecules in any substance as long as we know the number of moles. So we can relate moles to grams using that average atomic mass, and we can relate moles to number of atoms or molecules using Avogadro's number. Okay, example 2 says americium is an element that does not occur naturally. It can be made in very small amounts in a device called a particle accelerator. Calculate the mass in grams of a sample of americium containing 6 atoms. So in this case, our known is 6 atoms of americium, and our unknown is grams. So in order to do this kind of a problem, we need to change atoms to moles. So we're going to need Avogadro's number, and we need to change moles to grams, so we're going to need the molar mass. So I start with my 6 atoms. And because I can't go directly from atoms to grams, I need to change that to moles first. So I'm going to use Avogadro's number to do that. We know that 1 mole is equal to 6.022 times 10 to the 23rd. And then after we've converted that to moles, we can use the molar mass to convert it to grams. So we look at our periodic table. We find americium, which is 243 grams per mole. That cancels out moles. We'll wind up with grams. So we do 6 times 243 divided by Avogadro's number. And we wind up with only 1 sig fig, 2 times 10 to the negative 21st grams as our final answer. Okay, example 3 says aluminum is a metal with a high strength to mass ratio and a high corrosion resistance. Calculate the number of moles and the number of atoms in a 10-gram sample of aluminum. So we're given 10 grams. The first thing it wants us to calculate is the number of moles. So that'll be our first unknown. In order to go from grams to moles, we need the molar mass. So we set up our problem, and then we look up the molar mass of aluminum on the periodic table, which turns out is 26.98. That's going to go on the bottom because we want to cancel out grams. And then we can just do our calculation. So we had 3 sig figs in our known, so our answer should also have 3 sig figs. So we wind up with 0.371 moles of aluminum. Our second question is asking us to find the number of atoms. So it would be a good idea, instead of starting with grams, to just start with this moles that we've just calculated, because we can't go directly from grams to atoms, but we can go directly from moles to atoms. So for our known for this one, we're going to use this number we just calculated. And for our conversion factor, to get from moles to atoms, we need to use Avogadro's number. So I'm going to start with the moles, 0.371 moles of aluminum. And then I'm going to use Avogadro's number to change that to atoms. So remember, there's 6.022 times 10 to the 23rd atoms in 1 mole of any substance. That cancels out moles, and we can just calculate this in the calculator. And again, 3 sig figs, so we should wind up with 2.23 times 10 to the 23rd atoms of aluminum. So the molar mass is the mass in grams of 1 mole of any substance. This is also the number on the periodic table. We call that the atomic mass But it can also be used as the molar mass. We just have different units for it when we call it molar mass. And most of the time we'll use molar mass, but when we're discussing isotopes or individual atoms, oftentimes we consider it in terms of atomic mass. Anyways, the molar mass can be used for compounds as well. So we can add up the atomic masses of each element in the compound. And we also have to multiply that number by the subscript. So like H2O, we would have the molar mass of H times 2, because there's a subscript of 2, plus the molar mass of 1 oxygen. And so you just add those up to find the molar mass of any given compound.
Example 4 says calcium carbonate is the principal mineral found in limestone, marble, chalk, pearls, and the shells of marine animals. It's giving us 3 things to find. First, we want to calculate the molar mass of calcium carbonate. Then we need to find the mass in grams of a sample that contains 4.86 moles of calcium carbonate. And lastly, we want to find the mass of carbonate ions present in that sample. So the first thing we need to do in order to calculate the molar mass is to figure out the formula of calcium carbonate. So we know calcium is Ca. It's a metal, so this is going to be an ionic compound. And so calcium has a charge of 2+ based on where it's located on the periodic table. Carbonate is one of our polyatomic ions. Its formula is CO3 2-. So when we look at this, we wind up with those two canceling each other out. And so our formula is CaCO3. So to find the molar mass, we need to add up calcium, which is 40.08, plus carbon, which is 12.01, plus 3 oxygens, which are 16.00 each. So I add those up, and I get 100.09 grams per mole. I'm going to write that up here so we can remember it. And then I'm going to erase this so we can do the rest of the problem. Okay, question 2 says, what is the mass in grams of a sample containing 4.86 moles? So we have 4.86 moles of CaCO3. We want to find how many grams that is. And so anytime we're going from moles to grams, we need to use the molar mass, which is what we found in the last problem. So we take our 4.86 moles and we plug in our molar mass in order to cancel out moles. And then we can just multiply there to get our answer. Our known had 3 sig figs, so our answer should as well. So we wind up with 486 grams of CaCO3. So I'll write that up at the top here too. Okay, the third and final question here is asking us to find the mass of carbonate ions present in this sample. So we found the mass of the CaCO3, but actually let's start with the moles here. Because we want to separate this out into just the carbonate, and the easiest way to do that is to go back to the moles. So we want just the mass of the CO3 part of this. So we're going to need basically like a mole ratio kind of inside of this compound. and also the molar mass of CO3. Okay, so first off, we have our moles of CaCO3. We look at our compound and it's a 1-to-1 ratio between calcium and carbonate. And so we can say that there's 1 mole of CO3, that carbonate ion, for every 1 mole of calcium carbonate. That changes us from moles of CaCO3 to moles of CO3, which gets us one step closer to our answer. Then we need to figure out the molar mass of CO3. So we add up 1 carbon and 3 oxygens, giving us 60.01 grams per mole. And now we can calculate it. And we wind up with 292 grams of CO3. Example 5 says isopentyl acetate C7H14O2 is the compound responsible for the scent of bananas. It is also the compound that bees release when they sting, attracting other bees to join the attack. A typical bee releases about 1 microgram. How many molecules are present in the bee sting, and how many atoms of carbon are present? Okay, so we have our compound C7H14O2, and we're dealing with 1 bee sting, which is about 1 microgram. The first question asks us how many molecules are present in the bee sting. So, in order to do this problem, we need a few conversion factors. First, we need to go from micrograms to grams because we can't convert micrograms to moles. So we know that 1 gram is equal to 10 to the 6th micrograms. Once we have grams, we'll need to convert to moles in order to get to molecules. So we'll have to use the molar mass of this compound. Finally, to get to molecules, we'll have to use Avogadro's number. So we start out with our 1 microgram, and we're going to convert that to grams. So we can cancel out micrograms. Then we need to use the molar mass to change it to moles. So because we want moles, that 1 mole is going to be on the top. And then we can use our periodic table to find the molar mass of our chemical formula here. So we have 7 carbons, we have 14 hydrogens, and we have 2 oxygens. Giving us 130.182 grams per mole. That lets us cancel out grams. And then lastly, we need to find molecules, so we're going to use Avogadro's number, 6.022 times 10 to the 23rd molecules per mole. So we can go ahead and do the math here. And we wind up with 1 sig fig, 5 times 10 to the 15th molecules of C7H14O2. Okay, so then the second part of the question asks us how many atoms of carbon are present. So let's write this down up here. So we have 5 times 10 to the 15th molecules. That's going to become our known. And our unknown is how many atoms of carbon are in that number of molecules. So we have 5 times 10 to the 15th molecules of C7H14O2. And when we look at our chemical formula, there are 7 carbons in each molecule. So 7 carbon atoms in one molecule. And then all we need to do here is multiply. And we wind up with 3 times 10 to the 16th carbon atoms.